Lamborghini fans, and welcome to today's episode, which is an engineering guide to buying bicycle wheels. Now, next to sorting your position out and then sorting your clothing out, the next best low-hanging fruit to go and annihilate are your wheels. Now, in the current market, there's loads of wheel manufacturers out there, and it's not possible for everyone to test every permutation. So this guide will give you some of the tools and some of the things to look out for when you go and buy a new set of wheels. Now, before I go any further, I must give you a bit of a warning, and that warning relates to reviews that you may find online on websites and manufacturers' data. Now, websites that are various cycling publications, they're quite often paid in one format or another to do reviews, and you can usually spot these because these review sites don't give anything less than about 3.5 stars out of 5. They often accompany wheel reviews with stuff like they accelerate well, they hold their speed well, they climb well, but without any objective numbers behind them. I would suggest you ignore them. The other thing is manufacturer data. If you are going to go and have a look and base all of your buying preference on the manufacturer's own individual data, I would suggest that is ill-founded. There has been a trend in the past to put wheels into wind tunnels, which is a mathematically inert environment where the flow hitting the wheels is perfectly straight on and you don't have any deviations or anything like that, unless it's a transient wind tunnel. But out in the field, out in the real world, you've got street furniture, hedges, and wind itself does not come in straight lines. So bear that in mind when you are about to purchase. Now, a few little caveats before we go forward. You need to pick the right wheel and tyre combination for your bike. Now, you need to consider whether you're going to run tubeless, which is like this tyre on the right hand side. It's a laminar wheel with a Continental Grand Prix 5000 tubeless tyre fitted, or this type, and this is just another example, which is a sort of more conventional tube tyre with a clincher tyre on it. Now, I usually run this is my preference, because it's just much easier to live with on a daily basis, and then when you're in the middle of nowhere, it's much easier to fix. If you have an issue with this, generally you'll need an air compressor to reseat the tyre, so it becomes a bit more tricky. Now, as a key point around brake discs and rim brakes, I've just shown you a rim brake wheel, but this one is a disc brake wheel. The industry as a whole is trying to move towards disc brakes, and I think this is mainly for commercial reasons rather than engineering reasons. If you do require discs, then be aware that you'll have a weight penalty, because the mounting hardware is obviously slightly heavier, the wheel itself has to be heavier, the bearings are heavier, and you've also got what's known as a pumping loss. And that's because this rotor has to remain cool. If it doesn't, then it will start to warp. So you have these slits in here and here. The slits on the outside are there to improve the heat transfer coefficient, and they generate turbulence. That is how they work. Generating turbulence has an aerodynamic loss, so there's that bit. The other thing is, on this particular rotor, and it doesn't affect all of them, is this is an Ice Tech Shimano rotor, and it has slits in here. The idea of those slits is it sucks air up from behind and then forces out this way, and that is a pumping loss. So if you put the wheel directly onto an axle and spun it, it would actually slow down faster than if you took the disc off, and that's mainly because energy is absorbed in here, and that is not an insignificant loss. Now, plenty of people say you can shield the brake disc from most of the drag. That's generally a load of rubbish, because if you shield it, then you will reduce its ability to get rid of the heat, and if you do that, it will start to warp. Now, to give you a bit of background, most of these wheels are manufactured in China, more specifically in Xiamen. They're often sold as OEM rims to a Western wheel builder, and then they will put their name sticker on it, a bit like the laminar wheels, and then call it their own wheel set. Now, Far Eastern manufacturers are catching on to this. So this wheel set, which is extremely popular, it's a Windspace Hyper 50, they are now selling directly via websites, AliExpress, all of those things. Alternatively, you can actually buy the rims, the hubs and the spokes, and then build the wheel yourself. And finally, I guess the other example is you can get an OEM spec wheel. Now the larger companies like Zipp, Bontrager and others will build the wheel or have someone build the wheels to their specification with their own layups, rim profiles, and then sell them as that. But you do pay a premium for that. So we've got two wheel sets here. We've got a 56mm Fast Sports wheel and a 38mm or 40mm Elite wheel. Now rim depth, which is measured from here to here or here to here, depending on how you want to look at it, is probably the biggest differentiator between wheel sets. Now the rim depth has a direct influence on the aerodynamics of the wheel set and the accumulated weight at large radiuses. So the weight that's accumulated here basically and here as a ring donut will have a direct influence on how fast you can accelerate, turn and brake the bike. That weight also affects the ride quality in something known as noise, vibration and harshness. That's a bit more of an in-depth topic than for today. Now a good choice for a day in, day out rim is around 50mm, so something like this. If you're time trialing or if you are at a steady speed, something that's 65mm or higher would probably be best. And indeed, if you are time trialing, a rear disc will be ideal. Now for crit racing, where you need the acceleration and the ability to take corners, you're probably better off with something slightly shallower. Now, if all variables are kept the same, the deeper wheel set, so in this case this one, will always be more aerodynamic. This is mainly because there's a larger control area, so a solid boundary on this one. So there's less space for mixing and turbulence to generate. You also have an improved alpha critical angle. Alpha critical angle is that angle there. The shallower that is, the faster you will be able to go because the air will separate less. Now on something like this, which is the laminar wheel, that alpha critical angle is quite tight. It's very blunt, as you'd probably call it. So it separates quite far up on the cord. These graphs show you the correlation between rim depth that is plotted on the x-axis and power absorbed that is plotted on the y-axis. There's 50 km per hour on the left and 30 km per hour on the right. The relationship is quite clear. A deeper rim is faster. There are a few outliers, but generally they follow the same pattern. The one notable one is this outlier here. This is a tri-spoke wheel from Farsport/AliExpress. This is a fundamentally different concept, and the large aerodynamic saving comes from the spokes or lack of them, and there is a significant drop in pumping or mixing losses. Rim profile. There isn't generally much to be gained from the rim profile in isolation, but there are some factors that need to be looked at. Now, alpha critical angle has already been mentioned, and it's effectively that sort of taper angle off the edge of the rim. And another thing to consider is the transition between the tyre and the rim, which is located here. You either want that to be very clean or trip. Now, many people speak about the 105% rule to ensure the rim is 5% bigger than the tyre width. 105% is excessive. It's better to have the rim in line with the tyre, i.e. 100%. If this isn't possible, then a slightly bigger wheel rim to prevent light bulbing is ideal. Now really you want to look at the tyre and the rim as an assembly in this situation. A very good rule of thumb that is used frequently in aerospace is the 25% rule. A very tolerant and aerodynamic core to thickness ratio is 4:1, and that is why NACA 0024 aerofoils are so well studied. I've drawn what this means on the diagram, and the tyre must be included in the equation. Generally speaking, for a tyre that measures up at 23mm, you'd need a rim that is around 50mm deep. That will give you a thickness to chord ratio that exceeds the 4:1 ratio. If you go up to a 28mm tyre, you would need an additional 20mm of rim depth, i.e. a 70mm rim to compensate for the increased thickness of the profile, and you can see that in this superimposed picture up here. You should also note that if you do that, you'll also make your bike sit fractionally higher relative to the road. The only real variations in rim profile away from the transition to the brake track tend to be around how blunt the trailing edge is. So that's this bit here. This is generally referred to as a toroidal rim profile or U-shaped rim profile. Aerodynamically, aerofoils will have significant flow separation. It's colloquially called a stall, but it's technically not correct, around 12 degrees. So that means if you're going in a straight line, air is coming at you from around the 12 to 1 o'clock position. Doesn't really matter what shape it is, it will separate around the same number. Now, a toroidal is not actually that aerodynamic. A pure teardrop shape is far superior, but it has some structural challenges, like the ability to attach the spokes. Now, the advantage that the toroid allegedly gives you is improved crosswind stability. This is a bit of a disputed area of aerodynamics. Crosswind instability or twitching is the result of pressure buildup on one side of the wheel, followed by a sudden collapse. So, for example, if you were to get a large amount of wind coming from that side, what would happen at some point is that air would suddenly move to the other side, and then you would get the twitch. Now, that twitching is a product of the pressure differential generated and the surface area exposed, and therefore a deeper rim has a squared relationship. So just a small increase in the rim depth makes it much less stable in crosswinds. Stability is fairly controllable up to about 50 millimeters, and from there onwards it's like an exponential increase. Now, in terms of generic rim profiles, what you want to avoid is late bulging, so this kind of thing, and probably that kind of thing as well, so, and even that one. What is better is this type, so it's heading towards a normal teardrop. Now, those late bulging type rims, I've never seen it work on wheels, and wheels that do employ that kind of strategy tend to perform badly. You don't gain anything. The more pointy the trailing edge the wheel has, it'll ultimately be faster. My general guidance is to ride the deepest wheels that you can get away with, i.e. if you can get away with an 80mm wheel and a disc on the day, then do so. Now, you may see various posts from people claiming that wheel X is better than wheel Y in crosswinds. Just bear in mind that the instability is almost all front wheel instability and is heavily influenced by the rider weight, angle of the head tube, and the effective length of their stem. A longer stem provides more damping and stability, but that's not really a topic for this video. Now that brings us on to the spokes. Now, fewer spokes that are wider will generally be faster. So if you can get a tri-spoke wheel, that'll be the fastest thing to get. Now, a popular type of sort of flat bladed spoke is the Sapim or Sapim CX-Ray, which this laminar wheel has fitted. They are steel spokes and or metal spokes, and they just use conventional nipples. They're a very tried and tested design. A newer trend is to go to these sort, which are very flat bladed wide spokes that are made of carbon. This is way more aerodynamic, but they do have, well, some of them have a problem. So I had a set of wheels from KPS and Ascent where the spoke detached from the threaded section and came loose, and then I crashed. Now, budget wheels tend to have round spokes, and there's really nothing wrong with these from a structural point of view, and wheels have been made using this type of spoke for years, but they are associated, again, with budget wheels these days. There is an aerodynamic penalty for round spokes, and it's about 3 watts at 200 watts. So, you know, that gives you an indication. Now, nipples are another area of aerodynamic loss. So some wheels have no nipples on show. So some of the Yoleo wheels are a notable example. So the problem with those is general use is a bit of a problem, general maintenance, because you'll have to take the tyre, rim tape, all that kind of stuff off, because you need to get in from this side to adjust any spoke tensions. Now, this wheel, this laminar wheel, has quite a large amount of spoke nipple or nipple on show. And that's easy to maintain because you can get a nipple key in there, no problem. At the other end of the spectrum, well, the other end of the spectrum is probably the YOLO wheel, but this Fastbox wheel is a kind of halfway house. So you've got the ease of maintenance because you've got a small amount of nipple showing, but it's not a massive amount, so the loss is kind of minimised. Again, these things are small, but they cumulatively add up. Now we come on to hubs. Now, a major selling point for hubs is the number of engagement points that a hub has. So it's usually a multiple of the number of poles in the ratchet, so in this case 4, and the corresponding number of teeth that are in the wheel hub. It's a bit of a con, really. You don't need such a fine tooth engagement on a road bike compared to a mountain bike because you're not really in such a low gear. Generally, this part of the assembly isn't going to make much difference because you aren't pedaling. Now, once you are on load, the more important characteristic is rolling friction and associated hub stiffness. There can be quite a lot of flex generated in the hub from the bearing clearance, so that's the gap between the inner and outer races in there. There are really only 2 designs of hubs, those that use loose angular contact bearings, so basically Shimano, and everybody else who uses deep groove ball bearings. So this is a Fast Sports wheel that uses their own hub. This is a laminar wheel that's got a DT Swiss hub in. That's quite a popular one. Now, the big disadvantage with cup and cone is that once the mating surfaces wear out, they can't easily be replaced. You basically have to buy a new hub. Bearings will always wear out, irrespective of what you might read on the internet. Now, Shimano hubs in particular can be a bit of a pain to set up because they're quite sensitive to preload. The other thing to note is that the rolling drag on a loose ball bearing, so a Shimano hub, is usually more than something that's based on cartridge type bearings. Now, hubs that use deep groove ball bearings vary quite considerably. It's best to get a hub with the largest bearings available. So in this case, for practical purposes, the largest you can get is generally a 17mm axle. So that uses 03 size bearings. So that bearing in there is a 6903. These 2 bearings inside the free hub are 6803. That 03 indicates it's 17mm. Now, some budget hubs, such as those found in Hunt wheels and others, use quite slender axles. This is marginally better for drag, but mechanically it's not recommended. I'd also point out, if you are using a front disc brake, the bearing loading on the front wheel is much higher than a rim brake, as the brake load is an offset. So you will be advised to get a front hub with a large bearing, in this case something like a 6903, so something on there would need a bigger bearing than the rim brake equivalent. I'd also avoid anything that uses non-standard bearings. So DT hubs quite often use 15267 or 18307 bearings in them. They'll inevitably wear out, so you are going to have to source bearings, and you're going to have quite a limited supply. The rolling friction is quite adversely affected by the fit and alignment of the bearings inside the enclosures. Now, there have been many reports and videos on this channel of eccentric bearing arrangement. This will slow you down. It's not really possible to check this before you buy the wheel, so it is well worth looking at independent reviews to see if they have any issues with wheel bounce. One of the most common failure modes for bearings is corrosion, and this kind of attracts people towards stainless steel bearings. Stainless steel will still corrode, but it'll take much longer in a harsh chemical environment to do it. Now, the big disadvantage is they have much higher rolling friction and are softer than hardened steel bearings, i.e. the cheaper bearings. So they tend to deform, and if you get contamination into the bearing, you'll cause galling. If you sprint a lot, you really want to avoid stainless steel. Some large hub makers that you will probably find on your internet research is Bitex, Novatec, DT Swiss, Carbon TI. There's a few others, but they're the main ones. Quite a few of the wheel manufacturers actually specify their own hubs. The manufacturers of them tend to be an OEM. build quality is something that can't really be judged before you buy, but I'm including it anyway. Internally, the wheels can vary quite considerably. Here we have some Ascent and some Just Riding Along wheels. I mean, you can see this kind of creasing or tenting. And what that is the carbon layers have grouped together, and there is a layer of epoxy underneath, or a void, and this makes them much weaker and susceptible to failure. This is an Elite drive wheel, and this is, you know, far better manufactured. This is a Hunt wheel and another Hunt, well, it's a different Hunt wheel, and you can see here two examples of fairly mediocre manufacturing. So we've got circumferential and radial defects. So that's a radial defect and that's a circumferential defect. That looks to be the result of fairly low temperature epoxy that's been used to cause that blistering. Now, this kind of failure can put you in hospital, so it's something that you want to avoid. And that brings us to the end of this wheel buyer's guide. If you did enjoy it, remember to press that like button. If you do have any comments, whatever they are, please use the comment box below. Thanks, and until next time.